A steady ratio. One little equation. Watch it appear.
Watch the scene first. The math is built into the world, so the quantities can be seen before they are named. Our guide is this river otter, navigating the wetland current. By following the animal's physical actions, we can track exactly what changes and what stays fixed. This etched river stone shows the master template for proportional relationships, y equals kx. Here, k is the constant of proportionality. It's entirely fixed. The y and x are variables, representing quantities that fluctuate as the otter moves. Writing a proportional equation is simply a process of finding that hidden, unchanging constant and locking it into this universal template. Our first context is a direct unit rate. As the otter sorts these bundles, we see that bananas cost $1.80 per pound. This row of shells shows our constant of proportionality. Because we have a per-pound rate, k is handed directly to us as 1.80. We substitute that value into our base template, giving us the equation y equals 1.80x. When you start with a per-one rate, the equation can be assembled immediately, without any complex calculation.
The rate stays constant. Every pair obeys it. One rule holds all.
The otter moves a set distance for each marker on this shell path. These smooth stones are etched with the pairs 2,7, 4,14, and 6,21. To extract the constant from this path, we isolate one pair. We take the y value of the distance and divide it by the x value of the otter's bundles. Dividing 7 by 2 gives us 3.5. With the constant discovered, we drop it right into the proportional form to write y equals 3.5x. Testing any pair in a proportional table with this specific division will reveal the exact same hidden constant. 14 divided by 4, or 21 divided by 6, both confirm our constant is 3.5. Look at the natural coordinate grid formed by these currents. Try to picture how you would set up the division for the otter's position at a graphical point located at 5,12.5. As the otter passes this specific current mark, we find the x and y values anchored right here on the stretched reed. We follow the same mathematical step. We divide the y value of 12.5 by the x value of 5, identifying a constant of 2.5. We plug 2.5 back into the base formula, painting our final equation, y equals 2.5x, onto the shell. A spatial graph functions exactly like a visual table. The method for extracting the constant remains identical because the otter's movement follows the same proportional rule. Whether the data arrives as a unit rate, a path of stones, or a crossing of current ribbons, the structural mission is the same. This environmental layout shows our three completed equations side by side. The notation on these surfaces records how the movement through the crossing translates into specific, unchanging quantities. Before we finish, look closely at the physical space. Which mark in the environment proves the mathematical relationship, and how does the animal action make it true?
One equation held all. The rate never wavered. Write one for yours.